So, to lecture 26, I welcome you all. Now, today what I will be telling is that after getting some idea about your various kinds of voltage sources, current sources, this, that, today I will be telling you how to find out the steady state solutions and importance of that. See, for example, we now know that we have seen, suppose consider a simple RL circuit, series circuit R and L. I told you that if you have connected a source which is suppose sinusoidal V s t is equal to V max sin omega t, and I tell that the switch is closed at t equal to 0, this switch. That means, if this is the supply voltage, if this is the supply voltage, this is your V max or V m, I was writing V m. So, if this is the supply voltage, then and this axis is either time or omega t, time, t or omega t, it does not matter. If it is t, then this for our supply system in our country, frequency is 50 hertz. So, time period is equal to 1 by 50, which is equal to 20 millisecond. These numbers you must remember. So, this total time here is 20 millisecond. Now, if you close this switch at t equal to 0 and I want to know what will be current, the expression of the current behind all those mathematical steps, forcing function, natural response, it will be like this: V m by the solution will have two components. One is the steady state components, omega square L square, into, it was obtained earlier with longhand calculations, minus theta, where this part is the steady state parts, I steady state solution. What is tan theta? Sorry, tan theta, where tan theta is omega L by R, reactance by resistance people call it, and this part is called the impedance of the circuit. Now, there will be another part, the natural response, and the natural response is the current must start from, suppose I 0 minus was 0. Therefore, current must start from 0. Therefore, at t equal to 0, steady state current will be how much? Steady state current will be at t equal to 0. So, I t total solution, steady state current at t equal to 0 will be this much, V m by root over r square plus omega square L square, t equal to 0, it will be sin of minus theta, is not? Therefore, a current must appear to make it 0 at t equal to 0, a term like that, and then e to the power minus r by L into t. This will be the solution, and this I can write by inspection. I expect you to develop this kind of reasoning, because after all current has to start from 0. So, this is the steady state current. Steady state current will be lagging the supply voltage by this angle theta. by this angle theta. Now, this amount at t equal to 0, the steady state demands that this current flows. Put t equal to 0 in the steady state solution, this is the current. But I am once again telling current must rise from 0, because I have closed the switch at this point. Therefore, there must appear another DC current of same length. So, negative of the steady state current at t equal to 0, and that thing will decay exponentially. So, this plus this will give you the total current in the circuit. After few cycles, only this sinusoidal portion will remain, because this will exponentially decay down to 0. Is that clear? Therefore, people often are interested to know what is the steady state value of the current when a circuit like RL is excited with sinusoidal voltage sources. Knowing fully well, okay, when you close the switch, there may be some transient current introduced into the circuit, but that transient current is not going to last long, because order of the time constant of the circuit may be few milliseconds. So, after few milliseconds or so, maybe 2-3 time constants, this portion will not be there. So, this is the steady state part, and this is the natural response INT. So, INT natural response will vanish to 0 after some time. Some time means you cannot leave it like that, you better say after few time constant. Understood? So, steady state current, then who suppose you have energized your fan in your room, machine accelerates, there are some transients initially, but after that everything is in steady state, current drawn from the supply is only sinusoidal. So, who bothers about that transient which lasted for few milliseconds initially? That is the idea. So, the question therefore now comes that, okay, if I am interested for the steady state solution only, I am interested only this part of the solution. This natural part of the solution I will not care. Of course, this term is important in case of fault analysis in power system circuit. In day to day work, it may not be that important. For example, how much will be your electricity bill? You do not bother about this term. It is this steady state current and steady state voltage that will grossly decide what will be your electricity bill. Transients are born whenever you do some switching in presence of some energy storing elements, but they will also decay down faster, because in every circuit there will be some resistive elements. It is not that only inductance and capacitance you are switching on. Therefore, R will be there, so everything. So, if we are interested in steady state current only, then is there a simpler technique to do that? to do that. See, it looks like that you have a circuit which may not be as simple as a simple RL circuit. There may be series, parallel, so many energy storing devices will be present, and for example, a circuit like this or inductance, here are capacitance, here is another R, inductance, another R, and you close the switch. At some t equal to 0, Vs is V max sin omega t. Then if you close the switch, there will be some transient phenomena definitely taking place in this, which can be elaborately solved from the differential equation, solve it. And from that you conclude that okay, the transient part will decay down to 0. Transient part will appear where? In this current and voltage across the capacitor, is it? But those transients will go. Ultimately, you have excited the circuit with a sinusoidal voltage source like Vm sin omega t. Everything will be only solution due to forcing function. So, that is why people were always thinking that okay, if we adopt AC system for supplying power, to solve a circuit involving several energy storing elements in association with some resistive elements, every time I have to write down the differential equations, then I have to find out okay, natural response I will not do, because that will not be present in the steady state, it does not matter. But nonetheless, to find out the solution due to forcing function, we have to replace this sinusoidal voltage in terms of e to the power j omega t, e to the power minus j omega t. Even that calculations will become tedious when a complicated circuit like this is to be solved, even for steady state alone. That is what I want to say. Can there be some ways of simplifying that matter? Yes, it can be, and that is called the Phasor approach. If we are interested in steady state solution alone, that is ISST, which is IFT, forcing solution due to forcing function. When the supply is, that is a condition, you cannot do for any supply, for when the supply is sinusoidally varying, time varying quantity, like VST is V max sin omega t, like that. What is omega? Omega is 2 pi f, f is the supply frequency. So, if we are interested in steady state solution alone, when the supply is sinusoidal varying, then Phasor approach is adopted. Okay. It can be done only for sinusoidal. That is, you need not write the differential equation then say okay, steady state solution is like this. That is the point I want to make. Now, the question is what is Phasor approach? Okay, for the first time let us consider a circuit like this. This is very interesting. RL, and here is a supply voltage. We have connected like Vm sin omega t. Okay, and I am interested to know IT. IT means ISST, only steady state current I want to know, because I know this switching transient, that is the solution due to natural response, is going to die after some time. So, I am only interested in the long run what remains in the circuit. Only VST will remain and only ISST will remain. This S is the supply voltage to indicate that. Therefore, I know I have solved differential equation and I have come to this conclusion that this is your supply voltage and then your steady state current, which I will call IT only, although it looks like. So, this is Vm divided by Z into sin omega t minus theta. This I have got natural response, forget it, where Z is equal to root over r square plus omega square L square. And what is theta? Theta is equal to tan inverse omega L by r. This is the thing, this is known. Okay, with this thing known, what is Phasor approach? Okay, for the first time you have to solve it classically like this and got this one. Now, before we go to the Phasor approach, we know this much. Suppose you have any time varying, we will come back to this a little later. Let us go to next slide and say that suppose you have a time varying quantity, say A1 sin omega t is a sinusoidally varying time quantity. How to represent it at phasors? How to represent it? Represent it as phasor, Idea is very simple. What do you do? Okay. Draw a circle, this is the center, and imagine a length A1. This is called phasor and it is moving in the anticlockwise direction with speed omega radian per second on this circle. This is the position of the phasor, at t equal to 0. What will be the position of the phasor at any arbitrary time t? Position of the phasor at any time t, this length, it is moving with speed omega and it was at t equal to 0 horizontal, it must have moved this angle. So, position of this phasor will come here. What is the length of the phasor? I have taken it to be the amplitude of the sinusoidal quantity. What is its amplitude? A1. So, this will be the phasor. Okay, now why it is called phasors? Because what you do is this now, draw a vertical line to the t equal to 0 position, it has gone there. What will be this intercept? This length will be how much? A1 sin omega t, is not this length from this right angle triangle A1 sin omega t. At therefore, this A1 sin omega t, although I have imagined that a length is moving like this, I will be back in my mind thinking that okay, at any position A1, the projection of A1 on this vertical line will give me the instantaneous value of this sinusoidal quantity. At that time, at omega t equal to 0, it was like this. What will be the projection of this vector on this vertical line? Omega t 0, no. So, this is the point. At time t, so here what I will do? I will do omega t. At any omega t, at this time, it will be there. So, this is the time, omega constant, so omega t. So, you will generate this sine wave. After some time, it will come here. Then, when it will be vertical like this, then you will get the peak value. Got the point? So, the relationship of the instantaneous value and representing it by a phasor with constant length A1, this has got a 1-to-1 correspondence. Got the point? Therefore, I will draw like this. Suppose you have got another phasor A2 sin omega t minus pi by 6. Suppose you have got another phasor. So, this is one phasor, this is another phasor. What is the angle between them? Pi by 6. Therefore, if this is A1, omega t equal to 0, it was lying here. At omega t equal to 0, A2 was lying. So, this is the positive direction of measuring angle, anticlockwise, positive angle with reference to this reference line, horizontal line. Therefore, this is A1, it was fine, but at t equal to 0, this phasor also moving with omega, and depending upon its magnitude, the radius of the circle will be set. So, this is the position of this vector A1 sin omega t, this phasor, and at that time this was the position of this vector A2. And both of them are moving with a speed omega. Mind you, phasors you can only represent for same frequency. You cannot represent two sinusoidal quantities, one with 50 hertz, another with 25 hertz on the same phasor plane. They must move with that angle, and this angle is theta. And what is the idea? Idea is that you draw a vertical line here. So, it will give you this will give you a sine wave like this for this voltage, this will be the sine wave with amplitude A1, and for this quantity it is lagging this by theta. So, whatever is happening to A1 now, after theta it will happen there. So, similarly projection at omega t equal to 0, it is not 0, it is something here negative, but for this projection is 0. This side is omega t, oh my god. So, this side it is having a negative value, a2 sin minus theta. Therefore, at instant to instant I can also sketch this, and you see a2 is this one. So, it will go there and come back. Got the point? It is lagging. So, this angle will remain intact theta between these two. Therefore, any sinusoidal quantity with any angle theta, I will be able to represent it by thinking that there are lengths, fixed length corresponding to the peak amplitude of that sinusoidal quantity moving with speed omega, and if you are calling it to be sin omega t, that is you choose as reference, okay, and the other quantities with respect to this can be just drawn. And it does not matter whether after understanding this I draw a1 like this and a2 like this angle theta. I will always okay a1 sin omega t, then draw the vertical there. So, this picture can be rotated because relative velocity between them is 0 and theta is a constant thing. That is the whole idea. Now, without telling much right now, let us see about the voltage and current waveform of an RL circuit. You have applied with sin omega t, you have got the response of the current like this. So, these are sinusoidal quantities of same frequency omega. So, I will represent the voltage phasor as Vs bar. A bar is put, a phasor quantity, and capital letter supply voltage phasor. If you do it, then your current phasor will be lagging this by an angle theta. This is I bar. What is the length of this? What I am telling, length is Vm. What is the length of this? Vm by z. That is what I am telling. And both of them are moving with speed omega. This is omega, this is omega, and this is theta. Got the point? Therefore, the angle between the phasors will remain time invariant, it will remain constant. What is that constant? Omega L by R, this is the thing, omega L by R will be the constant. And these phasors, I am telling, yeah, I could draw it also like that. How does it matter? Bs, I will draw, but this fact is true. I bar, this is theta. Both of them is moving omega. So, this is the beauty. Then I will take, okay, this is reference vertical, that component I will take there. See, one point must be understood clearly. Your supply, listen this point carefully. Suppose you have a supply available at your socket in your room, plug point. Here there is a sinusoidal voltage existing. Now, how this is existing here? Okay, it is doing like this supply voltage. Sinusoidally it is there. There is no time attached to it as it is, but only thing it is attaining some peak value 0, negative peak 0, positive peak, and it is going on doing. Now, when you how to, what is the equation of this voltage waveform I want to write? It is totally my problem. Supply voltage is doing like this. If I say that I will write down, I want to write down this voltage equation when voltage is 0 going towards positive, then I will write this equation as V max sin omega t. Somebody may say that I will write down the equation, this will be my omega t equal to 0, and when the voltage is maximum and reducing, that instant I will start counting my time, and then I will write this as V m cos omega t. And if you choose this as origin, somebody else will write it as V max sin omega t. It is totally your business. Supply voltage is going on doing like this. Similarly, somebody says, I will take this neither 0 non maximum this point as my t equal to 0. Then the equation of this one with respect to sin omega t will be, it is leading sin omega t plus theta. I think you have got the point. But nonetheless, whatever be the supply voltage, by what angle current will lag, that is fixed, that is the angle theta, clear. Therefore, now the crucial point, one point I will just make, this is the time domain expression of the supply voltage. This I will write it as a phasor, and I will attach it as an angle 0 degree, because this is my reference phasor. Then I will say my current, this is VST, everything is real in our day to day life, nothing complex. IST, IT, steady state current, IST, it is equal to some Bm by Z, that is Im into sin omega t minus theta. Then I will say, if you represent this as Vs angle 0 degree, represent this as Im angle minus theta, it is lagging. Now, this is one way of representing. Now, remember this Vs 0 degree, it is essentially Vs 0 is nothing but in complex domain, it will be Vs into e to the power j omega t, j omega t. Similarly, Is minus theta is nothing but Im, not Is, I, the system current, I is equal to Im and e to the power j omega t minus theta. In complex plane, you see, if you assume this to be your real axis and this to be your imaginary axis, then this has got Im, this is at any time t, if you go, it will move by omega t, this will also move by omega t, and this way it can be written. It is a particular position at omega t equal to 0, these are the position of the phasors. So, we will continue with this in the next class, and the most important conclusions then we will be able to draw. Thank you.